And so let's start with discussing the solutions of our fifth homework now. So first, for the first question, we ask you to, sorry, not pi, but phi. So we ask you to compute phi, the Euler phi function with 720. So we know that 720 is equal to 2 to the power 4 times 3 to the power 2 times 5. And then we know all of its prime factors, and we get 720 is equal to 720 times 1/2 times 2/3 times 4/5, which is equal to 192. So this should be easy for you. And question 2, let n be a possible integer and d be a factor of n. So how many numbers x are there with x is between 1 to n and GCD xn is equal to d? And then prove that this summation is equal to this summation, which is equal to n. So for the first part, how many numbers x are there with 1? 1 is less than or equal to x, which is less than or equal to n, and GCD xn is equal to d. So we know that GCD xn is equal to d. Then x and n are both divisible by d. And GCD x divided by d and n divided by d is equal to 1. So this question, how many numbers are there, is equal to how many numbers x divided by d are there such that x divided by d is between 1 divided by d, but which is less than 1. So, but it's an integer, so it should be greater than or equal to 1, and less than or equal to n divided by d. And GCD x divided by d and n divided by d is equal to 1. So the number of x divided by d is equal to phi n divided by d here. And then we want to prove these equations are true. So for the first part, so let's say the divisor of n is d0, d1, d2 to dn. We know that dk times dn minus k is equal to n if we arrange them from the smallest to the largest. So we know that the summation here for all the d, phi d is equal to the summation of all d here, but it can be replaced by the one of the other d. So it can equal to the summation of phi n divided by d. So from part A, we know that phi n divided by d is the number of integer x between 1 to n, and GCD xn is equal to d. And we are summing out all the possible d that can happen in here. So we can get the sum of them is equal to n. So is this part okay? So the I is playing it properly.
So for this question, do we have Simon?
Huh?
Do we have an example for this question?
Sorry, I didn't prepare. We can write in.
N is equal to 12, and then let's try to do that.
Okay.
Do you want to do that?
Okay.
Let me do that.
Okay.
So let's try n is equal to 12. So what are the divisors of 12? So what are the divisors? So which number can divide 12? So possible divisors include 1. 1 is a divisor, right? 2 is a divisor. 3 is a divisor. 4 is a divisor. Maybe 6. Put it here. So the divisor. 6 is the 4 is a divisor. 6 is a divisor, and 12 is a divisor. Am I correct? Okay. And then now we are trying to to partition the numbers 1, 2, 3, 4, 5 up to 12 into different groups depending on the GCD with 12. Okay, so which numbers between 1 to 12 has GCD equal to 1 with 12? So GCD, the number x, 12, let's say is equal to b. So what are the numbers here? So 1 has GCD 1, right? 2, 3, 4, 5. Is it okay? And then 7, 8, 9, 10, 11. So these 4 numbers has GCD equal to 1 with 12. Okay? And then what are the numbers with GCD 2 equal to 12? So 2 is a number, am I correct? And then 3, 4, 5, 6, 7, 8, 9, 10. So just these 2 numbers. Is that okay? How about 3? How about 3? 3 is 3, right? 4, 5, 6, 7, 8, 9. So 3 and 9. These are the 2 numbers, right? And then how about GCD with 4? So let's write down again GCD of x and 12 is equal to d. Okay. So what are the numbers? So 4 is a number, and then 8 is a number. Am I correct? And then 6 is just 6. 12 is just 12. Is that okay? Okay. So if we put the numbers here, then each number from 1 to 12 appears exactly 1. Okay. And then
你要关前面的灯。
now there are 4 numbers here.
黑板对吗？
1, 2, 3, 4. So how many numbers are there? So of course we know it is 4 numbers, but then these 4 numbers, there are 5, 12 of them. Because these are the 4 numbers that has GCD 1 with 12. Is that okay? And how about this one? These are the numbers that has GCD 2 with 12. So how many of them? So if they have GCD 2 with 12, then let's divide it by 2. So divide the whole work everything by 2. So you get this become 1 and that become 5. And these 2 numbers are those numbers that has GCD 1 with 6. Okay, so how many numbers are there? So there are altogether 5, 6 numbers here. Is that okay? Is that okay? And then how about this one? 3 and 9. 3 and 9, they have GCD 3 with 12. Okay, so we divide the whole world with 3. So this becomes 1, this becomes 3, and these 2 numbers are with GCD 1 with 4. Is that okay? So how many of them? So there are going to be 4 of them. So there are 2 numbers here. So how many? So there are going to be 3 of them. Is that okay? And this one, there are going to be 2 of them. Is that okay? And this is 1 of them. So in that sense, if we add up the 5 of 1, 2, 3, 4, 6, 12, it adds up to equal to 12, which is the value of n. Is that okay? So this is amazing. So this works for every possible n, as long as we consider all the devices and take the corresponding file. Okay? Good. That's it.
Okay, so for question 3, so let P be a prime number, and assume that A and B are integers not divisible by P. Establish the following. First, if A and A to the power P is congruent to B to the power P mod P, then A is congruent to B mod P. So for the first part, we can just use the Fermat's Little theorem. So A to the power P is congruent to A, and B to the power P is congruent to B. So we know that A is congruent to A to the power P, which is congruent to B to the power P, which is congruent to B. And for the second part, if A to the power P is congruent to B to the power P mod P, then A to the power P is congruent to B to the power P mod P squared. So the hint we give you is, first we assume A is equal to we know that A is equal to B plus PK for some K. And then we want to show that P squared is divides A to the power P minus B to the power P. So we just compute A to the power P minus B to the power P. Here we get is B to the power B plus PK to the power P minus B to the power P. And we know we are using a binomial theorem here. And the J equal to 0 case is equal to B to the power P. So we delete J is equal to 0 case. And for J equal to power 1 case, which is equal to this part, we get P choose 1, which is P, times B P to the power P minus 1 times PK. We have P here. So this part is divisible by P squared. And for this part, we have J is equal to 2 or more. And here we have PK to the power J. So this part is also divisible by P squared. So we know that A to the power P is divisible by P squared. And hence A to the power P is congruent to B to the power P multiplied P squared. Is everyone okay with this part? Okay. And for question 4, in this question we want to show that 2 to the power n is not congruent to 1 modulo n for all n is greater than 1. So here we want to prove one property, then use the proof of contradiction, assume that this one is actually false. So 2 to the power n is actually congruent to 1, but we find out there is a contradiction. So hence the initial assumption is false, and hence this is true. So for part A, prove that if n to the power j is congruent to 1 mod n and n to the power k is congruent to the 1 mod n, then n to the power GCD jk is congruent to 1 mod n. So by the property of GCD, we know that GCD is jk is equal to aj plus bk for some integer ab. So we can write n GCD jk is equal to n to the power aj plus bk. And as we can see, this one is equal to 1 and this one is equal to 1. Sorry, congruent to 1. So we know that the test name together, we all get 1. And for part B, so assume for the sake of contradiction that 2 to the power n is congruent to 1 mod n for some n greater than 1. Using the result of part A, show that 2 to the power GCD p minus 1 n is congruent to 1 mod p. So first, by Fermat's theorem, we know that 2 to the power p minus 1 is congruent to 1 mod p. 2 and p are, GCD 2p are 1. It's 1. And we know that n divided 2 to the power n is congruent to 1 mod n. That means n can divide 2 to the power n minus 1. And we know that p is a factor of n. So p can divide 2 to the power n minus 1. So 2 to the power n is congruent to 1 modulo p also. So with the result of part A, we know that 2 to the power GCD p minus 1 n is congruent to 1 under modulo p. But what is the contradiction here? So we know that p is the smallest prime factor of n. So GCD p minus 1 n is should be equal to 1, which means 2 to the power GCD p minus 1 n should be 2 to the power 1, which is congruent to 2. But by part B, we know that we get that 2 to the power GCD p minus 1 n should be congruent to 1. So these two things contradict to each other. So the assumption we make first, 2 to the power n congruent to 1 should be false. That means 2 to the power n should not be congruent to 1 modulo n. So is everyone okay with this proof? Okay. In question 5, we ask you to decrypt this cipher text where the public key is 211 and 2419. So first, n is equal to 2419. We know that it is equal to 41 times 59. And second, we want to compute phi n, which is equal to 14 times 58, which is equal to 2320. And E is equal to 211. And we want to find a D such that E times D is congruent to 1 modulo phi n. So I don't have a very good method or systematic way to find D now. Oh, Euclid. So just find the.
So let's divide. Yeah, let's do this again. Let's do it together.
Okay, sorry.
So we want to find out what? Modulo 2320, right? So we want to find out. So we want to find out some value of x and some value of y, such that 11 times x plus 2320y is equal to 1. So if we can find this case, then in that case, if you mod 2320, the x value will be the inverse of, sorry, we're not doing 11, we're doing 211. Is that okay? Will be the inverse of 211, modulo 2320. Is that okay? And then, this is the GCD of 211 and 2320. So what we can do, so we try to write down whatever, so we can write down 211 and then 2320 here. Okay? And then, so you can think of this number as a number A and this number as a number B. Is that okay? So for 211, it is equal to 1 times A plus 0 times B. And then for 2320, it is like 0 times A plus 1 times B. Is that okay? Okay? And then we can do find the GCD by doing Euclidean algorithm. So we take we deduct the maximum multiple of 211 from this one. So how many can we do that? 211, 211. Okay, so we can deduct 10 times of 211. Is that okay? So 10 times of 211 is equal to 2110. Am I correct? So it is like 10 times of 2110 is 10 times of A plus 0 times of B. Is that okay? And what is the result? Okay, the result of this one is equal to 210. So if I want to express 210 in terms of AB, then it is like this one minus this one. So it is like minus 10 and 1. Is that okay? Okay, good. Okay, 211, 210. So I should deduct 1 times of 210. So 1 times of 210, according to what we have done, it is equal to minus 10 and then 1 here. Is that okay? And so we get the result. This is the one that we want. And what is this one? According to this one, this is equal to 11 minus 1. Is that okay? So what we have done is we got 211 times 11 minus 2320 times, okay, or plus this one times minus 1 is equal to 1. Okay, so this is the inverse of 211. Okay, that's
Okay, sorry.
okay.
So finally, we have to compute to decrypt this text. So to decrypt, we just have to find what this text to the power 11 under modulo n. So we can get the text. The numbers are actually equal to 17, 101, 114, 109, 97, and 116. So this should be the answer. And if you wonder where we get these numbers, so I just type from mask and convert it to ASCII code.